Okay, so hello everyone. My name is Po Kim. I'm an assistant professor in the School of Mining Engineering and Mineral Resources at the University of Arizona. So before I introduce today's speaker, I should say that he is not only a giant in our field, but also someone I often joke is like a father figure and a mentor in rock mechanics, whether he knows it or not. So it is a real pleasure to introduce Dr. Peter Kaiser, one of the world leading authorities in rock mechanics and underground excavation design. His work has fundamentally shaped how we design and operate deep excavation in highly stressed ground, particularly through yieldable support system for managing rock burst hazard. He has received numerous prestigious awards from Canadian and US rock mechanics community, including the ISRM Leopold Mueller Award, widely regarded as the highest honor in rock mechanics. So please join me in welcoming Dr. Peter Kaiser.
There we go. Thank you, Juliet. Thank you, Bo, for your introduction. I guess he called me a mentor, but if you have enough white hair, I guess you become an elder, and maybe that's what you should have used rather than a mentor. Anyway, it's a pleasure to be here and to talk to you about from common to best practices in underground rock engineering. Bo was referring to Mueller, was actually the Mueller Award that inspired me to talk about this topic. That's many years ago. This talk is updated to problems that we have today, but the issue is still the same. So the storyline, okay, the story, can we get rid of that black line there? Click, okay?
Yes.
Okay. The storyline is relatively simple, but when we go through the slides, you will find some of them are technical details are maybe beyond your area of expertise. I was originally a civil engineer. I know there's civil engineers here, but my area of expertise today is deep underground rock mechanics, where you have rock bursts and instability. And so some of that field may be not that familiar to you. But the message is valid independent of your area of expertise. For rock engineering or robust rock engineering, you have to take account of the complexity from geology. You have to integrate it into effective construction processes, as well as you have to consider safety aspects as well as cost efficiency. And to get that right, we really have to, as engineers, work to get the rock mass behavior, how the excavations underground behave right. And we have to apply state-of-the-art engineering principles and newest technologies to get the best out of our engineering projects. And one principle in engineering is if you cannot measure it, you can't really use it. So one of the things that I will focus on is best practice means to design that you actually can check your design by measurements of some kind. If you have energy that can't be measured, and that's your design criteria, then you have to ask yourself, are you designing on fiction or on reality? So basically, if we use common practices, we have to evaluate, are there any efficiencies in those practices, and if necessary, change and adapt them. And really the bottom line of this talk is, this is the responsibility of every engineer. We have more standards in civil engineering, we have very few standards in mining, so it's down to the engineer that has to make sure that the practice that he adopts is actually applicable. And so let me go through some examples. It's said that 1,000 words or a picture is 1,000 words. And when you look at these pictures from different mines that you see listed there, you have to ask yourself, what is the lessons you learn when you go underground and you see this? And one of the lessons that you obviously get, there's large deformations in each of these pictures. So something went wrong and there's a lot of deformation. The rock moved in either violently in a rock burst or steadily by squeezing. If that's the observation for a practicing engineer, that means you need to think of how can I use deformation as a design criteria? And how can I use deformation to verify that my design is appropriate so this doesn't happen? So to overcome these type of problems, we obviously have to, when that happens, you know something went wrong. So whatever we did to these excavations isn't working. And so you have a common practice that led to the support design or the design of the excavation. But if it's not working, then something has to be flawed or ineffective. You have to come up with a hypothesis of what is wrong and how can I fix that problem. Then you have to verify whether your new idea or new way of doing it is working properly. And then you come up with a better or best practice that in the ideal world, you then take back into common practice, and I'll comment about that. So the talk today is basically all about something is wrong with common practice. What do we need to bring it to best practice so we then can make it standard or improved practice in engineering? So back to these pictures, if we realize that we have large deformations, and today we have technologies like LiDAR surveys, the picture on the top right, we can measure deformation. And we realize that deformation is the problem. So good practice must bring the two things together. And at the bottom, we developed methodology called deformation-based support design. And I'll explain to you why that is relevant. So how do we design as an engineer? First, we start with a problem. Then we select some kind of a design model. In a building, maybe a wind load, and a dam, it's an earthquake loading, etc. And you have a model on how to design the dam or the slope. Then you pick design parameters, material parameters, or engineering design parameters. You specify some kind of a methodology to get a safety margin or to define how severe the potential implications are, and you come up with a solution or a mitigation of a problem that you're dealing with. So in slope stability, these circles are, first of all, we have different failure mechanisms, and the engineer picks one of those mechanisms as the applicable failure criteria, circular slope failure. Next point is you determine what are the material properties, strain weakening properties, or whatever, and you put that together to come up with safety factor, as in the diagram there, and you come up with a solution that either changes what you have been doing or defines the slope angle, etc. Now, in recent years, or about a decade ago, huge advances in slope stability were made by having radar allowing us to measure the deformation remotely. And so you had the ability to numerically model and at the same time observe what is happening in the slope. And that led to tremendous advances because you could now design and verify that your design is actual real. And if your design didn't work, you could anticipate the failure because you saw the deformations or you can see the deformations earlier. In underground engineering, the same applies. If you design a tunnel, you have stress fracturing around the tunnel as illustrated here in this cartoon. You have a depth of failure. You can monitor how deep the failure is. And then you have to ask yourself, what is the engineering design factor? Well, if you think of a rock as illustrated there and you stress it, what is happening? It fractures and it bulks. Just like when you blast rock, its volume increases, it bulks. When rock bulks, then it deforms because it can only go one way into the excavation. And the end result is an example here from a mine in Chile, which shows you that the deformation that is generated by the bulking rock behind the support has obviously destroyed the support and led to the failure here. But now we also have the ability in underground mining to use LiDAR information about the deformations before and after, or as mining progresses, and therefore we have the opportunity to make a step change in underground engineering design by designing for deformation. We don't need to design for what I call fiction. We can design for what we actually can measure on a daily routine basis. So we have to ask ourselves, if we have pictures like this, what went wrong? Did we not characterize the rock properly? Did we get the geology wrong? Did we calculate the stresses wrong? And we have more stress and the excavation fails. Did we not understand the failure process? Did we design the support wrong, as you can see in the lowest picture, is failing? Or was it an operational problem? We plan things and the operators do things different. So that, of course, is always an option. So what went wrong, or what is wrong in the practice that was used at all these mines that led to solutions which obviously are not acceptable, are unsafe, costly, and highly risky, not just to people, but to an operation. So if we have common practices that lead to this, how can we assess the hazard of working underground? You obviously can't, because things don't work the way they do. So here's a list of a few examples of what can be wrong. In red, what I think is wrong, and on right, what is the hypothesis to improve it. Rock mass characterization, and some of you have learned Q, RMR, GSI systems, and so on. What is wrong is it's a numbers game. Design has become centric on calculating a number and then coming up with a solution. The understanding of how the rock actually behaves is now hidden in a number, and the consequence is that in practice we get something different than what we anticipate. Also, most of the classifications are based on all outdated data. Civil tunnels at relatively low depths. Today we go to 2,000 meters, 6,000 feet, or whatever that is. The rock behaves different at that depth, and the data that was used to establish the classification is no more applicable. The failure modes, I call it modelers' hobbies, far from reality. Modelers and computer guys, and I know every student likes to become a numerical modeler, is fiction unless you know reality. And therefore, when you model something as a yielding thing, something behaves like butter, but in reality, it explodes and fractures, then your model is fiction and nowhere close to reality. I'll come to that point more, but another thing that is a problem is that the stress calculations that the numerical modelers, not just students, but consulting engineers do, many times is fiction. They calculate the wrong stresses and the answer is wrong. When we design something, people believe that what they have done in the past is what the future is about, and they do the same thing. And again, when you come from 1,000 feet depths and you go to 6,000 feet back, what you learn at the top is useless when you get to the bottom of a mine at 6,000 feet. And beliefs is not good. You have to be able to measure that what you actually believe is reality. And so when you get to hazard assessment, you have to have a systematic way to design, measure, and verify, and then you can assess whether there is a low or high hazard in a project. And I'll get back to this. Now, in the Miller lecture, and you can download the video or watch the video or download the PDF of the Miller lecture, covers a much wider spectrum. From now on, I'm going to focus mainly on bursting ground in conditions at depths where the failure mechanism is actually in a dynamic form and the excavation basically explodes. And I will cover three aspects. I criticize classification, so I explain why. I will talk about verified design approaches, deformation-based support design, and then I end with how do you bring this all together to have a much improved practice in engineering. So let's start off with the first principle, and that is how do we deal with the complexity of the geology? First of all, we need to understand the geology because you cannot make the rock fit your design. Your design has to fit the rock. And if you don't understand the rock and its behavior, your design will likely fail. And this brings me back to Professor Miller's talk in 1963. He was the father of the Institute of International Rock Mechanics in ISMR. And he wrote in 1964, describing the construction material, the rock mass in our case, in its condition and in its behavior is the first task before you deal with any large projects. And so now as then, more than 60 years later, it's still true. The most important thing is properly describe the rock mass and its behavior. So let's have a look at that. What do we do conventionally? We calculate a number. I was part of developing the GSI with Everett Hook. So it's a self-criticism, but you calculate a Q number, an RMR, or any other number. And the question is, are these classifications appropriate to solve your problem? Clearly, from the tone of my talk so far, the answer is clearly not. And I hope to explain in more detail why. But the main reason is the number doesn't tell you how the rock behaves. It tells you it's good ground, it's bad ground, but you don't know what background does. Does it squeeze? Does it blow up? What is the behavior of the rock for that specific number? So if we use classification systems, we have to use it for one single purpose, and that is to get the behavior of the rock right, not just whether it's good or bad. And you have to ask yourself, if I get a number, how accurate does that number have to be? Do I care whether it's an RMR 50 or 60? Is there any different material difference in my design? So we try and answer that question. So I say at the top, it's always good to learn from the masters. Terzaghi and soil mechanics, of course, very well known. In 1964, established a rock classification system on the left side, and they said it's massive, blocky to very blocky, it's disturbed in the lower class. Then we have Q system, Barton and Bianowski, RMR, and the end result is the same thing. If you look at the yellow boxes, the top it's Q, on the left side it's RMR, but there's basically three types of behavior. Massive, blocky ground, I call them rock mass class, quality class 1. In the middle, it is blocky or very blocky, and at the bottom, it's basically soil-like, very poor conditions. If we look at the GSI after 50 years later, Hook and myself and others developed the GSI system, but if you look at it in a nutshell, it's the same thing. It's blocky up here. It's massive, blocky, and it's shear behavior. A different chart, a different way to calculate the number, but the bottom line is what it tells you or what you have to get out of it is a question, which box does it fit in? If in RMR or RMQ, rock mass quality 1, the rock is massive. What does that mean? It most likely is stable or near stable. And I may need some help, but not much. If I'm in blocky ground and very blocky ground, there's a good chance it's going to fall on my head, fall off ground. And if I'm in class 3, it's squeezing, it's large deformation because it's so lake and it's at great depths, so we get large deformation. That's what matters. It doesn't matter whether it's 50 or 60, it matters which class of behavior are you designing for. The second, maybe the biggest flaw is when you take classifications, they mix up rock with stress. But if you look at Terzaghi and Hook, they never mention stress. Why? Because rock has a strength and the stress brings the rock to failure. They're two different aspects that you need to consider. So therefore, we should not use stress reduction factors or any of that kind to modify the rock property. We should use the stress to tell us how is the failure mode changing. And so as you can see, that leads to the 9x9 matrix of stress leading to gravity-driven, stress-assisted, or stress-driven failure. Same rock in one column, but different stress conditions make it behave different. And so classification in a good practice is aiming at getting the behavior right, not the number right. So obviously then the answer to my question, are they sufficient, is clearly not, because they're not focusing on what the engineer needs to design the excavation properly, a good understanding of the potential failure mechanisms that needs to be resisted. Now I'm getting even into a little bit more detail, but Bianowski has done good work on stand-up time. Stand-up time is how long can you leave the tunnel unsupported before it starts to fail. On the vertical axis, to the left of the 1 day is rock mass quality 3. So if you're in rock mass quality 3, the right side of the matrix, you have 1 day to support your excavation. If you're on the right side in rock mass quality 1, it's massive rock, you have infinite time, you're most likely through the tunnel long before a stability problem comes. And in rock mass quality 2, it doesn't matter where all these dots are, that's where the rock needs help, needs support, because you have between 1 day and maybe 6 months to stabilize the excavation. Then you have the Q system by Barton. And if you look at it, it comes to exactly the same thing. On the right side, you have rock mass quality 1. And if you look at all the details, it says the rock needs no support, basically spot bolting, some local support if you have a fault or something goes through the excavation. If you're on the left side, rock mass quality 3, squeezing ground, according to the matrix, you need very extreme support measures, multiple layers of shotcrete, dense bolting, small excavations, all kinds of complicated stuff. But the middle, the class 2, is where the rock is blocky and the support, systematic support, can help it. So my view is when you use classification, you don't ask what is the number, you ask which class of behavior do I belong in, and at what stress level does my rock exist, and then you know the behavior and you design properly for that condition. Another point that we will deal in a second is classifications are for the condition of the rock today. In mining, the rock is loaded different in a month, in a year from today. And so to design support for conditions today is not what you're interested. Your interest is to design for somewhere during the mining cycle. So let me move then to 2 or 3 aspects of design once you have properly characterized the rock. And the first one is, what is a credible stress model? And as I referred earlier, students like to model, so maybe this gets you one message that you can take away. First of all, engineers like to think stress. Geologists think strain. Mountains are created by straining the earth. And when you read a geology book, it's all about strain. When you read an engineering book, it's all about stress. And the trivial Hooke equation says stress is strain times modulus. And I was joking earlier, Young's modulus gets in the way between engineers and geologists. But there is an important message. Rock is not being stressed. Rock is deformed or was deformed. So why do we create stress models? And consultants do that every day, where they stress the model and they end up with a stress profile as shown on the left, when we know that mine was not stressed in a sedimentary setting. So Kathy Kolinchuk at the RASM conference here in Cannes some 4 years ago presented what happens when you strain load the model. You strain it until you have the stress that you have measured. But what you can see from the two pictures, the stress distribution is entirely different and is not anywhere close what the stress model is when you introduce the stress rather than introduce the strain. More importantly, this is a picture from SRK, where a highly faulted rock mass has been strained. And because blocks can move and wedge in, the stress distribution is not uniform. It's highly heterogeneous, as you can see on that sample. And I'll get back to that. What is the consequence for underground? Also, here is an example of a rock mass that has dikes, stiff materials. And when you look at the vectors, the stress orientation changes drastically depending on where you are in the geological pattern. So the message that I like to leave you with is, if you're an engineer, think like a geologist and realize that rock mass has gone through a history of deformation, and that deformation has created the stress that you are interested in, and therefore in a numerical model, you need to reflect that, unless you're in a perfectly sedimentary world where the rock has just been loaded up with more and more deposits, which I think doesn't exist, certainly not in this part of the world. So once you have the stress right, and you're now sold on the matrix, and we need to ask the stress levels, we have to ask ourselves, other than in civil engineering where you build one tunnel, the stress is not constant. When we have an excavation, we have stress razors that are generated around the excavation, and those stress razors can take the condition of rock that was classified to be here to a higher stress level, because during the mining process, you increase the stress. Alternatively, you can have the opposite. And as in the cartoon model up there, there's areas where the model shows is de-stressing. So that means if it was classified to be here, now it's suddenly de-stressed. So it's actually behaving as if it is higher in the matrix. Or if it was stressed and then de-stressed, if you did damage to the rock during the stressing process and you de-stress it, it actually moves in a different class of behavior. So the engineer's responsibility is to figure out where is the rock on its path during the failure process. So if we look at rock bursting, which would happen down here, if the stress increases enough, you have enough stress around the excavation, it explodes, gives you a strain burst, and that is the condition you have when the red vector is valid. On the other side, if you have the vector going up, all your wedges and all the blocks that were confined are now suddenly unconfined. You shake it a little bit, it falls down, and you have a fall of ground. And now connecting that back to the picture that I showed you earlier in the strained model due to the jointing giving you high heterogeneity, and I put kind of a cartoon tunnel here. If you would drive this tunnel, you would end up at one point in strain bursting condition, and you would end up further down the tunnel in fall of ground condition. simply because you have stress heterogeneity and you have stresses that are changing along the tunnel and in mining even more over the life of a mine. So the engineer's responsibility, and I'm not going to read all the words in there, but the best practice is to practice for the condition that you anticipate. It's not a description of what the rock looks today. It's what is the rock going to look like when you have somebody underground or walking through that tunnel. So kind of the takeaway is, in my mind, classifications to get 3 rock mass qualities, 3 stress levels, a matrix that tells you what is the behavior, and an appropriate stress model that gives you the starting point for any design. That then takes us to the next step. So if I now know what the rock is doing and what I need to design, how do we design support? And there are 2 flaws that I want to touch on in support design. The first one is called ignoring support consumption, and the second one will be design for what you can measure. So if we plot on the vertical axis the load capacity of a support system, on the horizontal axis the deformation or the displacement the support experiences, as you deform the support, some bolts will fail and your load capacity decreases as it is deformed. So the installed capacity is much higher than what you get when your support is deformed. If in bursting ground, we can plot the energy capacity on the vertical axis and the displacement, and there is a paper that you can read on that. But the remnant capacity of the support system decreases as you deform it. Just think of it, if a support has an ability to deform 50 millimeters, after you deform it 50 millimeters, you can sneeze and it falls apart because you have used up all the capacity that the support had. So what are we going to design for? The installed capacity or for the remnant capacity after some deformation? That's called support consumption. In every mine, your support system is installed, mining occurs, and capacity is being used up. I'm not talking about corrosion or poor installation, but I'm using about deformation that eats away on the capacity, and at some point the support fails just because it's deformed. So how do common rock burst engineers design? They assume the demand is vertical and energy that comes from a seismic source, or they design for stored strain energy that is released. And they compare it to the installed capacity. When in reality, the path is not up energy only, it is energy and displacement. And the vector shows that you're reaching the capacity not at the installed capacity, but a much lower capacity. So the good practice is not to design and calculate a factor of safety for the installed capacity, because the factor of safety at the end of this vector is significantly lower. And so if we look at a picture that I showed you earlier, this is not because we had dynamic energy hitting the excavation. This is because we have bulking of the rock behind the support, high stress, volume increase, deforming the rock, and it's actually damage that is caused by static deformation due to consumption of the support capacity. And at some point, brittle shotcrete can't take it, it spalls, rock bolts fail. So this damage is not caused by ground motion, but by deformation. And therefore, factors of safety, as you're taught in school, calculating the installed capacity and calculating a load is a nice thing to do, but it is meaningless when it comes down to mining situations where the remnant capacity is less than installed capacity. And if the number on top gets smaller, it doesn't take a rocket scientist to find out that the factor of safety is much less than what you have calculated. So let's look at an example of a strain burst. What is a strain burst? A strain burst is a situation where the tunnel explodes because you have too much stress. On the right side, you see the same image. I think it replays. Unfortunately, nobody got hurt in this picture, but look at the right corner. What happened? The wall or the floor basically suddenly heaved. What happened there? You observe underground, the rock was highly stressed, it bulked, can't go outside, goes into the excavation, and if that happens quickly, displacement over time is velocity, that gives you an ejection velocity. Not by some kind of earthquake somewhere, but by the excavation failing on its own. So if we have a force, the rock bulks, goes into the excavation, the failure you saw sends a seismic signal. We can measure how fast that failure process was. And if we measure the displacement and the time that happens, we get the velocity. On the next page, I show you example. But here we go, measured. Displacement can be measured. The time it takes can be measured, and therefore we can measure the velocity. And once we have a velocity, we can calculate the energy. But we have measurable entities right from the beginning. So here is a case example where I say at the top, it's not just bad practice or common practice is not just bad practice, it's fundamentally wrong to relate the velocity of ejection to the ground motion from an earthquake or from a slip event that is generated. Here is an example of a mine where we have a whole series of events, and they are basically measuring the convergence, the sudden convergence of that tunnel as it is failing. From the scalar moment that the seismologists measure, we get the depths of failure, and from the waveform, we get the duration. And here is a plot of the duration and the depths of failure. So I know now I created, let's say, 1 meter of depths of failure, and I created that in 20 milliseconds. I can calculate the velocity. So depths of failure between 0.1, 2 meters, duration 15 to 35 milliseconds gives me a velocity of ejection between 0.5 and 3 meters per second. This is now measured, not estimated or calculated. And so the conclusion, therefore, if we want to move to best practices in dynamic support design, we have to use measurable parameters, use the seismology information, use LiDAR information so that we get both the energy component, displacement over time, and the displacement. And then we have the vector defined. And so that really means we have to design the support in the energy displacement space. And this is not common practice. So we have to find a way to get that into engineering practice such that we can get a proper design. Now, some of this may sound kind of academic to you, but if I know I've taken the variability of stress and rock into account, and I've calculated all my demands, and I compare it to design, and I have points that are beyond the design. What do I do practically to change that? If I reduce the displacement, if I support so I have less bulking, I have less energy, and I have less displacement. So the engineering solution is then directly related to the model that the engineer uses in the design process. So I said right at the beginning, some of the technical detail is, I'm sure, beyond what you have learned in the courses so far or in practice. But the point is, there are some fundamental things that are wrong in common practice. And as an engineer, you cannot just follow the book and believe that it's valid. You have to identify deficiencies and modify them. And of course, once you identify them, the question is, how does it get into engineering practice? 5 minutes. Okay. How does it get into engineering practice? I can't just say, here is Kaiser's method, and then all the engineers have to do it that way. That doesn't work, because if we kill somebody or have a coroner's inquest, they say, why did you believe Kaiser and didn't know what you're doing? So when you change common practice, you have to manage the change and bring it into practice. And again, there is a reference to a paper that is just coming out that gives you more of the detail. But fundamentally, what you have to do is integrate all the information that you have about the rock mass properties, the geometry of the excavation, the stress model, the ground support. Otherwise, you cannot assess the hazard. And most engineering approaches are not integrating all of this. And you need to quantify it. A lot of risk matrices are 10 people sitting around a room and saying, what is this? More likely, less likely, and so on. We need to quantify, and I jump a little bit through this more quickly. But what we have established is a methodology now that we have a demand estimation, the blue curve. We have a support capacity, the consumed support capacity, and the safety margin is between your demand and the capacity, SMU. With that, we can calculate a factor of safety. We calculate the probability of something exceeding the design, or what the annual probability of exceedance is. These are quantified values that the engineer can then use to plan a mining operation. And so, because this is pretty complex, we have worked with IMS, Institute for Mine Seismology, South Africa, and so on, to develop the capability to take the learnings from bad practice into good practice, such that we can implement it in complex mining geometries, as you see. The user defines everything he or she knows about the rock condition, and then you have to let your model at every point of your mine define what are the conditions. And I'm just going to quickly illustrate what you can see on this example. The colors here are only the maximum stressor on the excavation. If you have a numerical model, that would give you that information. But what you're interested is not just what is that information, what you're interested in is how does that stress evolve over time? Because it does damage to the excavation, etc. So what you're really interested in is what is the stress history at every point of the excavation over the life of the mine? What is the depths of failure that is generated over the life of mine? And what are the deformations because they consume support? Therefore, at every point of the mine, I want to know that diagram. Now, I can't keep that in my head. You have to have a tool to let you go to every point in the mine and say, at what time is that situation existing? So when you then look at the same point in that mine on a time scale, and you calculate the safety margin, which I illustrated earlier, the difference between the demand and the capacity, you see how it evolves, and in 2006, 26, it suddenly drops. That tells you your mine life is good up to that point, but now I have to worry about my support system. So, for example, factor of safety, when the safety margin is 0, the factor of safety is 1. When is that factor of safety coming? Good practice is not to calculate it at day 1 of your mine. Good practice is to know when is your factor of safety reaching your design criteria 1.5, or particularly when is it reaching 1, because that's when you anticipate to have collapse, and what is the probability of that happening. So good engineering is to have sound principles, but also translate them into everyday operations so that the operators can actually see what you have designed and what is happening. So that brings me to the second last slide, and that is we started off, we go from common to best practice. Now, as I mentioned earlier, you can't just say, I believe Kaiser, and that's how we design things. You have to be convinced, because a professional engineer is responsible for what you design. And you can't say, I designed it the same as everybody else, equally wrong, and I'm fine. Well, that's actually common practice in many consulting firms. As long as we do it the same way as the others do, we're fine. But that's not good engineering. Good engineering is to question what is flawed, come up with hypotheses, fix, and come up with a better practice. But then that method has to become not only best practice, but has to become common practice. Because only when it becomes common practice is it acceptable in legal cases, in insurance cases, etc. And this is the reason why with IMS we developed the methodology that you can change your design, but then you can demonstrate it in a mine setting to be valid. So the title really changes from common to best practices, but then from best practices to common practice. It's an ongoing cycle. And the people that are responsible are you as engineers, because nobody else that tells you when common practice is not acceptable, and nobody tells you when new ideas are good ideas and can be used. So back to my first slide, where I said, it's a simple story, maybe complex details here. You need to understand the rock behavior. You cannot do anything if you don't know how the rock behaves. Whatever you design, you have to be able to measure. If you can't measure it, you can't design. And to eliminate deficiencies, at the bottom line is it becomes the responsibility of the engineer to every time when you do a job to make sure that you're on that process and don't have a common bad practice, but are using common good practices or improving the practices. And we were chatting yesterday. None of what I talked today comes from GPT. It comes from a list of names and people that I have had the opportunity to work with, companies that have sponsored and collaboration with IMS. It's people that work together and learn together that make the difference. And you can see one name in bold that is sitting here who was part of the team somewhere back there. I don't know who loves me, but that sounds good too. Thank you.